Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with number 51 in chapter 14. So what we're looking at, we've got this motor here that's designed to pull this load up. And in the problem it says there's a 500-pound, it's applying a tension of 500 newtons here. That 500 is good anywhere along here, as long as these pulleys are relatively light and the bearings are working fairly decently. And the question is asking for the power supplied to the motor, and it's important that we're talking about to the motor, and I'll talk about why later, after this load has been lifted a distance of 15 feet. All right, so again, I'll talk about the to the motor part and the efficiency later. For now, let's talk about the analysis. So power. Well, power can be expressed several different ways. I'm gonna start with this: rate that work is done, which means it's equal to dW dt, where the work term is force times distance. So the power is d dt of force times, I'll just call this delta x, with delta x up. Now, if the force is constant here, we end up with force times dx dt, which is going to be the speed of this object. So I'm going to choose to use this form of power right here. And the reason is because the force, we know the force supplied by this rope, so in essence that's a given quantity. It's going to boil down to this, all right, the speed. Now, to get the speed, I think what I would do is use the work energy theorem. Imagine this being position 1. I'm just going to put a dot for the box. And then position 2 is after this box has moved up some certain distance. I'm actually going to go back and I'm going to call this position 2, and I'm going to call position 1 down here somewhere. And the box has moved 15 feet. Now, when we write out the work energy theorem, if I put a datum right here, the PE1 term is 0. The PE2 term is an MGH term. The KE2 term is going to be a 1/2 mv squared, because at this position this thing's moving. But you're going to have a work term that you're going to have to take into account. Now, what that work term looks like, well, it depends on how you define your system. I talk about some different ways here. If we define our system like this, let's talk about the different forces acting on that system. There's likely normal forces inward, and they may or may not be the same. I'll put it N1 and N2. These bearings are indicating no frictional forces if they're in good condition. These normals don't do any work anyway though, so we're not going to need to worry about it because the displacement is up and they make a right angle to both normals. Now, there's a pair of tensions here and here, and it's important to realize that these are different ropes. This rope right here and this rope are a different rope. That 500 pounds is good for this rope right along here to this point. So there's a 500-pound force acting up here. But right now that is an unknown tension. Now, what we could do here is this. We can get that tension if we redefine or we look at this system right here. Notice there's two 500-pound forces up, this unknown force down, and the mass of this system is small. That should allow you to calculate this force. You'll have 500 up, another 500 up, and unknown tension down equals MA. That's going to give that force here. I'm not going to tell you what it is in the video, I'll let you figure that out. Now when we do the work term, when we do work from position 1 to position 2, we're going to have a 500-pound force up for this tension times the distance 15 feet. That work term is positive because the tension is up, and so is the displacement. Then we're also going to have this guy right here times 15 feet. Again, that's a positive work term. And again, you can get the tension here by a free body of this system. Keep in mind that you've got two 500-pound forces up and well, I'll say unknown tension down. And keep in mind the mass of this system small compared to the rest of it. So that's one approach to get that work term. Here's another one that's even maybe a little bit shorter. Let me back up. The other thing you can do is we can define our system like this and cut right through that part right there. And the reason for doing that is that if we draw a free body now of this part of the system, we've got that gravitational force vector down. And if you look carefully where we cut it, these tensions, this is all the same rope. So every one of these tensions is 500 pounds as long as these pulleys are relatively small and the bearings are working. So we've got a 500 pound force up, another, oops, I'll just do this, a 500 pound force up here, a 500 pound force up here, a 500 pound force up here. This rope is now internal to the system. That force, the force in this rope is up on this part, but it's down here. The net force is 0 on this system due to that rope. So when you do the work term, you'll have 500. Let's do this. 500 plus 500 plus 500 is 1,500 pounds times the distance, 15 feet. We don't even really need to apply Newton's second law to this. We could. What we would get out of it's the acceleration, but we're not really going to need that, I don't think, because my purpose here was for the work term, remember, in the work energy theorem. So the net work is going to be 500 plus 500 plus 500, that's 1,500 pounds times the distance, 15 feet. That'll give you the work term. You wouldn't worry about this in the work term if you're using a potential energy term for the gravitational force. So you're going to write out your work energy theorem. And again, because of where I put the datum, 0, I'm pretty sure this thing starts from rest. This guy right here is going to be 1,500 pounds times 15 feet. PE2 is going to be an MGH term. KE2 is going to be a 1/2 mv squared term. You should get an equation here that you can solve for V2 and get a number out of it. That number can go here, and you'll be calculating the power output of the motor. Now again, the reason I use the word output there, the motor is applying this force. It's creating this 500 pound force, and the faster this rope starts lifting up higher and higher and higher, if that force stays constant, the power output is getting higher and higher and higher. And again, it's an output because as far as the motor is concerned, that's actually an energy loss. Now, there's also a power input here. This motor is plugged in. And here's where the efficiency comes in. The efficiency basically describes how much of this input gets to become an output, basically. So the power out is equal to the power in times the efficiency. So what that means, imagine the efficiency were 80%. It's not in this problem, just imagine it is. What that means is that the output power is going to be 80% or 0.8 times the input power and so forth. In this example, the efficiency is, where is it? 0.65. So in this example, the output power is 0.65 times the input. That should allow you to solve for the input power. So that should get everyone through that problem. Let's stop this here and have a great day.